Welcome back. Section 7-4. It is about integration of rational functions by partial fractions. Here we learn about using partial fractions to integrate rational functions. For instance, note 2 over x minus 1 minus 3 over x plus 5 is, well, assuming I have calculated this subtraction correctly, negative x plus 13 over x minus 1 times x plus 5, which is negative x minus 13 over, when I unravel this, x squared plus 4x minus 5. In other words, integral of the right hand side, so negative x minus 13 over x squared plus 4x minus 5 with respect to dx is, well, integration of the left hand side. Integral of 2 over x minus 1 dx minus integral of 3 over x plus 5 dx. Well, this is straightforward. 2 natural log absolute value x minus 1. Likewise, this is straightforward. Minus 3 natural log of x plus 5 plus a constant of integration. So notice, if I needed to integrate this and I didn't know this, then I wouldn't have approached here. So these are called partial fractions. Their combination, either addition or subtraction, results in the rational function that you want to integrate. Okay? So, what is a rational fraction? Recall, a function fx is said to be a rational fraction if fx is px over qx, where px is a polynomial of a certain degree, qx is another polynomial of certain other degree. So, what is a rational function? It is quotient or a fraction of polynomials. So, px is of degree n, qx is of degree m. If the degree of the numerator is less than degree of the denominator, we say that fx is a proper rational function. If on the other hand, the degree of the numerator is greater equals degree of the denominator, then we say fx is an improper rational function. When the function fx is improper, you may use long division of polynomials. Divide the numerator by denominator, you get a quotient and a remainder over the divisor. Alright. So Sx is the quotient, Rx is the remainder. For instance, you are asked to evaluate integral x squared plus 3x minus 7 over x minus 5, x plus 5 rather. So notice numerator has higher degree than the denominator. So you can use long division to divide the numerator by the denominator. You obtain a quotient in this case to be x minus 2 and a remainder of 3. What does that mean? This division is quotient plus remainder over the divisor. Integral of the numerator separates out, that's a polynomial, so it's straightforward. Here the remainder is a constant and I am dividing by a linear function. Its integral is straightforward. It's natural log of absolute value x plus 1 plus a constant of integration. So this example shows us that when you have an improper rational function, that is numerator has higher degree than the denominator or even equal, you can actually divide and get a remainder of smaller degree. The quotient is a polynomial whose integration you know. Therefore, it is enough to understand the remainder part. Okay? It is enough to study the proper rational functions. That is where the numerator has degree smaller than the denominator. So let us start with a function that is a proper rational function. Numerator has degree smaller than the denominator. Let's look at the first case. Suppose the denominator, that is qx, is a product of distinct linear factors. Distinct. In other words, qs can be factored into linear factors which are all distinct. In this case, well, px is simply, p is degree smaller, so you may as well call it the remainder. Remainder x over qx is, you have to write it with constants on the top for each factor. So, a1 over a1x plus b1 plus is another constant for the second factor, and so on until a constant for the last factor, and then proceed. For example, here numerator, oh, that should have been a 9, okay. Numerator is 4x squared plus 3x minus 9. Denominator is 6x cubed minus 12x squared minus 18x dx. So notice this is a proper rational function. Let's see whether we can factor out the denominator. 6x cubed minus 12x squared minus 18x. Looks like 6x is common in all. So when you get 6x out, you're left with x squared minus 2x minus 3. Okay. This factors further x plus 1 times x minus 3. In other words, look at the denominator. The denominator has distinct linear factors. X, x plus 1 and x minus 3. So I can rewrite this entire original function as a over the first factor plus another constant over the second factor, another constant over the third factor. Now, you combine this, so you have your original rational function. Make sure you have 9 in there. And this, how do we add fraction? Well, you multiply these a times the missing pieces plus b times the missing pieces plus c times the missing pieces. Now multiply it out. X plus 1 x minus 3 is this. 6x times x minus 3 is this. 6x times x plus 1 is this. Now multiply, that is distribute the a inside. Likewise b inside, keep track of signs. Likewise c inside. Now combine like terms. X squared appears in 3 terms, a, 6b and 6c. X appears in 3 terms, negative 2a, negative 18b and 6c. And lastly, constant appears, that is no x, just once. Now, this fraction is equal to this fraction tells us that the coefficient of x squared is equal coefficient of x squared. Coefficient of x is coefficient of x. Constant coefficient is equal to constant coefficient. Now, we want to just simply solve. I usually go through the simplest thing to go through. Negative 3a is negative 9, tells you a is 3. Once you have a to be 3, you just need to substitute here in the first two equations. 3 there and negative 6 here. So that simplifies our first two equations. Now this is a system of linear equations in 2 variables. Well, together, well, here I am dividing by 3 to obtain this. So add this with this, negative 6b, positive 6b cancel. I'm left with 8c equals 4, c is half, a is 3, c is half. Plug in either one of those and you get b equals negative 1/3. So you obtained your a, b, c. Once you have your a, b, c, you substitute integral of this is integral of these. Each term, notice linear denominator implies you get natural log. Natural log, constant of integration, and don't forget these coefficients continue. That's how partial fractions are used to solve integration of a proper rational function where the denominator can be split into distinct linear fractions. We'll continue with another example in our next video.